Thank you very much. Thank you. It's a pleasure to be here. This time in person. Last year I was here just on the webinar. Much nicer to come here. I will present an update on what we're doing since last year or last year and a half or so, just to give you some idea of the projects which are related to the things Mort was talking about. What is machine learning? It is essentially you try to predict anything that can be predicted. And there's no rules, like in statistics, that it has to be linear, that it has to be certain odds ratio. There's no rules, except there's one very important rule, and that is that when you build a machine learning model, you always have to build with data which is then different than the data you will apply for, because it's very easy to create models where you have a perfect prediction because you overfit the data. That happens also in regular statistics, but in machine learning we are very particularly sensitive to this. And so I will just show you a few projects. Some of them actually will be presented. One of them will be presented tomorrow at AHA. You can look at that oral presentation. Some of them have been presented as CCT, RSNA, and there's some papers. So just a mix of different projects, about 1 or 2 slides for each project, just to give you an idea what we're working on. And so this is a cardiologist here. So this is a very nice article by a cardiologist about machine learning. I found it. I'm a computer scientist and computer engineering kind of person, but I worked with cardiologists so long that I started to think a little bit like a cardiologist. I hope. I think it's very important. But I particularly enjoyed that nice review. And there's a very nice slide here showing a figure, which you can see. You have a patient, and the patient has certain features. So that's one way of looking at this. Could be blood pressure, could be some imaging result, and then you try to predict, for example, heart attack. And yes, okay, heart attack will be corresponding to those kinds of patterns. So a very simple way you could look at that machine learning is that you would put, like, let's say you have just 2 features. And you say, well, these people, like when they have this kind of combination of features, they don't have heart attacks. But these people here, they maybe have heart attacks. So you try to cluster and find what kind of combinations of feature will give you a heart attack. That's a very simplistic way. But actually, there is an algorithm which is called K-nearest neighbor, where you try in multidimensional space, you look like, what is the, like, in like your physician's mind, it will be like looking for some similar patient to which heart attack happened right after. So that's basically how computer works. So that's one concept is very interesting. The other interesting concept in machine learning, which we use a lot in all these papers I'll show you, is that we use something called boosted learning. And that is a very powerful feature, which very much works a little bit like you have different versions of the algorithm, or you sort of like try different approach and you try to find the best solution. But then maybe you change some parameters, you try like a different model, or sometimes even totally different approach, and you get some other answer. So you try to divide who is normal, who is abnormal. But at the end, you maybe have 3 or 4 or 5 or 10 different models. But then imagine if you had like 3 or 4 doctors reading the scan, and each of the doctors will give you a little different approach, and some of them will be false positive and so forth. But when you put them together, it always works out that you get a better result when you have this kind of multiple models. This is called boosting. So that's another thing we use in machine learning. And so this particular paper was actually using boosting technology to show this machine learning prediction. And this was 5 years, not 1 year. I wish we could do 1 year, but this is the problem is that you have less data. I fully agree. 1 year is very powerful. 6 months would be even more powerful. The problem is the amount of events you get. Yeah, but this is very, very so in this paper, this is a confirmed registry of CT scans where there was over 10,000 scans with suspected coronary disease, and we have various features. And you can't read it very well, I'm sorry, but there's like many features. One of them is age, of course. Age is very important in prediction in this case was prediction of death. And there's many features coming from the CT scan, so there'll be some stenosis and so forth. And so there will be some green features that the clinical feature, and blue will be the imaging features come from the images, and you mix these things together, and you do something called I mentioned this importance of this separating the test from results. So what we do here, we do something called tenfold cross-validation. We use it in all these methods. We take 90% of the data, we build a model, and then we test it on the remaining set. And then we mix it again, and then we will do another model, different model. We test it on another 10% of data. Then we stack it together. That way we can actually look how model works, always built from separate data, but we actually can evaluate it in a large method. This is a widely used computer machine learning technique. And when you see this, look at the results here. This is the machine learning boosted model. This is the Framingham risk score in predicting that. And those are the variables, segmental involvement scored and some segmental score from the CT scan. So look at the power of this kind of prediction when you can do it. And this is done, this will be, so how would you use it? You would have like a calculator, which you could just have all these variables somehow brought from the electronic health record, and it will give you a probability of death in this case. And the Duke index. So all those are sort of together, but this is a very powerful technique. And it was in 10,000 patients, so with about 1,000 events or so. So one thing I just want to show you too many statistical slides, but something we wanted to highlight. We always hear this split sample here in cardiology. People use. We'll take half of the data, we build a model, and then use the next half of the data, we test the model. So that's a traditional thing I see in JACC and all these journals, and that's what you can use for machine learning. But what happens is that we tested this. If we use different people, we just mix different people, and we say, okay, we use some other 50% different people, and we then test it on the different group. That's the kind of, this is in about 1,000 patients, we get that much variation. So variation is huge. So when you do this tenfold validation, you are sort of in the middle, and it doesn't matter which people you select and so forth. There's like some even more sophisticated method, which is even better. But basically what we're saying is that you should use these techniques, because otherwise it's really, your result is kind of random depending on which patient you put into this test and which patient you put into this validation group. So that's an important thing when you do this machine learning models. So the other way we could look at the data is kind of interesting. This is our recent paper in JACC Imaging, just came out, where we look at the 3-year prediction of MACE. So we're shortening it up a little bit, but this is a small sample. But here we can look at it when we build this model. We can then look at this machine learning score, which will be some kind of probability. And you see here we can have a very high probability of MACE, up to 50%. And this would be the actual observed, how many, in this percentile, like if we find this kind of percentile of people, 95th percentile by machine learning score, we can see what was the actual event rate in this group. And it was actually 50, close to 50%. So this is, we are matching what actually happened. The gray bars are what happened in those percentiles, and the red curve and the red dots will tell you what was the probability predicted by the machine learning. So this is the kind of technique, this is a kind of a version of the Breyer score. And this is one way to look at, how your model is showing the data. And so how can you use it clinically as a doctor? It's a lot of math and all this. How could you use it? So we think, well, for example, this was the MPI, myocardial perfusion imaging. So what you could do is you get a scan. You typically get your quantitation here, QPS, or whatever, like that we do polar maps. Then there's some various variables which can come from the computer. A lot of variables, like we have TID, we have ejection fraction, volumes, like maybe there's 100 variables which come from images automatically. You don't have to do anything. And then there'll be some data coming from the clinical, from electronic medical records. And then that will give you your risk. It will just give you like a bar, and just like a hurricane prediction or how you're showing, you predict, okay, well, that patient is pretty high. And so what's interesting here is when we look at this this method, is that people in this highest percentile of machine learning prediction, which, as you've seen, was matching very much what actually happened, 19% of them were called normal, like clinically normal scan and normal diagnosis. So that's a large number of patients. This is a small study we did, but it can show you the power that sort of sorting out these people who actually are at the high risk from the people who are not. That's pretty much what we are trying to do here. So this study will be shown tomorrow at the AHA sessions. I don't know if you can see it very well, but this data is from Dr. Blaha, and this is a large consortium with 66,000 cases with calcium scan, and there are some existing. So this is a very sort of hard to see here, but it's a very large data set with cardiac death and cardiovascular death. So it's 500 cardiac deaths and 971 cardiovascular death. And here is your ROCs, and here this is just an area under the curve. So you see the red one, the machine learning, with these boosted methods, comes up to 0.85 is the prediction of cardiac deaths. Is very high prediction of 12. This is a very long-term prediction, so we can, well, you know, but again, you can see that 1 year prediction is going to be under 50 events. But it is highly statistically significant from variables such as calcium score or this pooled cohort equation, the green one, which was shown before. They're all performing very well, but machine learning is highly significant, and it will give you a much more accurate answer compared to all these existing methods and also higher than the calcium score and the methods as used right now. We could also do machine learning on clinical data alone. So take out the calcium score, and that's the red, very red one here is the machine learning with calcium and the clinical data, and the one the brown one here is a little lower. It will be lower, but just very little. You can predict quite a bit from just clinical data alone. But calcium scan does add, even in this kind of large population with this latest machine learning, calcium will add. And you see here this Breyer scores again, how nicely it's calibrated. But you notice the event rates are lower because, so that will be something, when you start narrowing the exact death, what kind of exact event you're after, like myocardial infarction, that this event will be smaller. When you have MACE, there's a lot of MACE events. So the one question cardiologists often ask is, does it have to be a black box? Can I, like, the machine will give you probability and that's it, you have to believe it. So no, doesn't have to be black box, and we're just working on some techniques where it can give you some rationale, like telling for a given patient, not in overall, like we look at the model, but for a given patient, we'll tell you, okay, well, that patient has a high risk score, but it's because there will be like some kind of parameters, like a rational value, which will tell you because of his SSS and because of the age and because of the left ventricle enlargement and lung uptake and taking the digoxin drug. So it could explain to you why the score was high in some kind of quantitative fashion. So I think that would be one important thing, because the doctor would like to see what's going on. So those techniques can be available, like they are available in machine learning. So now going to this very fancy topic of deep learning, which we have started to work with right now, and it's kind of very exciting. Everyone talks about this. And this is, a simple way to explain is that we are trying to work with some kind of, mostly the images. We use it for images rather than like just the variables. And this has been applied before to these things you can look at the internet. There's this cafe, NVIDIA has this, and Google, they have this web packages where you can recognize, for example, is it a car, or what kind of car is it? And typically they have millions of images, over millions of images, but actually for each class of the image, like a Volvo car or something, they have about 1,000 images. It's not that many. So it's something similar to what we can actually obtain in our sort of research where I work. And one of the applications is I work with Dr. Day here at Cedar Sinai, and one of the applications we apply this now is to use it for pericardial fat detection from non-contrast CT, and so that there's a lot of research about it. That parameter could give you some additional value, but the problem is, it's very hard to segment these images and accurately. So there's various algorithms and there's like all techniques, but it's always a little manual, and then it takes a lot of time, and then people don't want to do it because this is it's a cheap scan. It's only $50 scan. So if you have someone has to spend 1 hour to analyze it, it's not gonna work. So you have to have some very automatic technique, which will just give you the result right away, and then you can maybe use it. And so these are the latest results. This is presented at SCCT, and we presented at RSNA. You see, this is the deep learning method. So in here, the deep learning, this is a sort of complicated network, which will be able to assign probability for each pixel. Is that pixel belonging to the pericardial fat, or is it belonging to the paracardial fat? And you can assign these probabilities. And this is the expert, grand truth of expert. The expert will spend some time doing this very carefully. And then this is a totally automated result. And you can see that these results are very high. The correlation is 0.93 for this red, for finding, the volume of this red pericardial fat in a totally automated fashion. What's interesting here is that we use this kind of deep learning network. We use this cafe. We use those graphics cards, those fancy graphics cards, which allow you to do process much faster. So we can do, the training takes few hours, but then, so you say that's very long. But for each patient, then when you have that model, it takes only 5 seconds to segment. So this is very fast actually to apply clinically, but it will take you hours to train it. So the question is, we don't have so many cases. There was only, there was like 100 or 200 cases. But the thing is that here you are testing on slices. So you're actually doing so it's different because here you only want to know per pixel, so per slice. So you can have many hundreds of thousands of slices, and you can train it even from existing smaller data sets. So that's how you use machine learning, sort of on a lower level, not going high to predict, but doing very accurate segmentation. And I think that would be like the input then to the next layer results. And something different is kind of between the image segmentation and prediction. We have just recently done and presented at ASNIC is the polar map. So we have in nuclear medicine, we can very accurately segment polar map results. We can have this is pretty much automated right now. So we get these blackout maps, and we have quantitative tools, and we get some very good results with this already. So can we, using this kind of new machine learning techniques, just squeeze out a little more of this data just from the images alone to start? Can we improve the accuracy? So using these deep learning techniques, we assign the probability score of the disease, obstructive disease, in LAD, LCX, and RCA. So we assign this kind of like some kind of a bar, probability, and then we have a patient score based on the maximum of this. And so when we do this, this is the sort of, and then we also enter gender here, because it kind of is a little, just like when you analyze images, you have gender-specific normal limits. So we enter gender here. And with this kind of technique, so using this kind of computer, my postdoc Julian Betancourt presented this. He has like 3 or 4 of these computers now around his desk. You can do it very fast. Training is like only 1 hour, but then it's only like less than 1 second per case. You can do very fast. And you can see, well, that's a small result, okay? But this TPD, we worked very hard for many years to make it really accurate. And now we can get like 5.4% improvement. That's quite a significant improvement, because there's no other data used here. It's only the same data, only the polar map. And so we're just starting with this. And then if we input better data into these models, we're going to get better prediction at the end. So here we work like sort of on a ground level with images. We try to get as accurate as we can. And that's what we are working on right now. We have a multi-site registry, so I just show you what we have here. This is supported by NIH. We have 20,000, almost 18,500. We will have 20,000 cases with MACE follow-up, and we have 2,000 cases with invasive angiography. This is quite a lot to do this kind of very accurate prediction from MPI at least. So that will be something if people want to then predict further, this will be a registry which could be used for many different applications. This is all on the very latest generation camera, and there's nine sites involved, and so we work very closely with all these sites here. So that's one of the projects we have. And another project, just to kind of mention, sort of different kind of thing, but can you use it for, and this is a future work, so I'm just saying what can be done. You heard a lot here at AHA about sodium fluoride. Group from Edinburgh, Professor Newby, they work with this. We work at Cedars-Sinai. And the question is, can you predict heart attacks with the sodium fluoride? But the question will be not just like have some sodium fluoride SUV or some value, TPR or whatever it is, but you have other information like CTA. You have many other factors. So So we're saying we want to predict it most optimal way. We want to predict it using this multimodality, CT angiography, all the nice plaque characteristics we can get from CT angiography, and then add sodium, and then use machine learning to really show if we can improve prediction of heart attacks with this. So those are the kind of projects I have, and I think at the end, doctors are always thinking, it's going to take our lives, but there's a very wise editorial from New England's Journal of Medicine where it says that patients actually will benefit the most. So if the patients benefit, I'm pretty sure the doctors will benefit, because you don't want to have unhappy patients. So this is all, and I just want to say that, in conclusion, the machine learning combines multiple imaging and clinical data points in one score. Deep learning can perform image segmentation. Machine learning can predict disease, intervention, outcomes in terms of post-test probability. And this quantitative computer interpretation will help clinicians to find the right answer for a given patient. Thank you very much.
So thank you very much. We also have a few questions. I want to stay on time, but I have one question about some of the work you've shown. So what you're doing with taking 10% of the data set is internal validation. You're taking a portion of a population and retesting it over the rest.
Right.
That's not considered the best method of validation. So your curves are very impressive. Well, your curves are very impressive, and I'm a co-author on them, so I can speak to this, I think. But you need to externally validate this against different sets. And all you've done, I think, is internal.
No, so let me just explain, because there's a little confusion about this, and this is very important. I don't know of many papers in cardiology which the true external validation is done, but there are some. The external validation is the following. We develop something. Let's say 9 sites. It's not really internal. We have 9 different sites. Okay. Now we develop in 9 sites, or for example, we then apply it. We find the 10th site who has nothing to do. Different people, different population, maybe a different time point. Maybe the best is if we even don't do it. We give them some tool. They run it, and that is a true external validation. That is very rarely done. Most of the time, it is like depending how you define it, but most of the time people will take some set, will divide it into like, okay, I take half of the population and then apply it to the next half of a population. That's an internal validation. But that, if you look at Jack paper, I just saw like a beautiful Jack paper with some machine learning. It was a simple, just dividing into half. And we're saying dividing into half, for example, or 70%, it's very random. And it gives you different results depending how you divide. So we're trying to average this dividing to make sure, we're pretty much doing split sample. We're just repeating it 10 times just to make sure that we're not giving you some random results. Could be good, could be bad, just depending how we divide it. But it is true that truly what you should do is to take, for example, 9 sites, test it in a 10th site. But, that is getting complicated with what kind of patients and so forth. But that is the kind of external validation, which is rarely done, but that is what we would. So we would build a model, then we'll give to people to do external validation.
But I think you'll need to do that
or we or someone else. But I think
you're going to need external validation, because I think if you look at your data, some would argue it's too good to be true. And it's too good to be true because you're validating it against your own patients.
Well, not really.
It's
but
definition of internal validation. You can say we don't do enough external validation, but you're doing internal validation, which is not the best way to do it. And there are ways of doing it. You could have taken the calcium consortium, and instead of taking 10% randomly, you could have excluded one site and left that as the external validation.
That is true. That is true. Yeah,
so you had the opportunity to do it that way. And I bet you could have done it on any of these, because you had 9 sites in the other study. You could have done 8 versus 1.
It is possible. It is possible, and we were looking in this direction.
The next step may be to now take your model that you've created and now validate it against a 10th cohort. Right?
I fully agree. There are some complications. For example, say there's like 9 is a small number. So, for example, they use a different camera, and then you question like, is it so? So there's some like practical complication, but it is true that is what we should be doing in the second round. So typically you do.
You need to see that, because we're not going to trust that it's going to work outside of your.
I agree. So maybe in that pooled cohort, if there's site information, we can look into this. We can actually maybe do that if the numbers are reasonable, because sometimes when there are this multiple sites, there's like some people add like very few patients, other side adds a lot of patients. So you get this kind of technical problems with this. But
I think it deserves external validation before we just accept the model.
No, of course.
It's wonderful work you've done, honestly, and I think it's really a next step. Please.
So from whatever naive perspective that I'm not coming from, I've never worked with deep learning and neural networks, but I have some background in genome pictures and all the linear predicting and prediction algorithms. And I would actually respectfully differ from what you stated in the sense that external validation, this is like external validation done 10 times. That's how I look at it. And whatever deep learning source that I have read it so far, they all back the fact that cross-validation is actually much better than doing external validation. And to go with your point of having tenfold cross-validation and have one external site or external data set reserved for external validation, I would argue that actually have 11-fold cross-validation by including that would actually give you even more robust results than having a single external validation.
But I think, actually Dr. Budov is right, because it is because like if all the patients was the same around the world, that would be fine. The problem is there will be some site and they have different people, they don't actually scan this kind of people. Or, their camera doesn't work, or some, there's this kind of reason. Or maybe they were scanned 5 years later and now the things have changed. So those are real world issues which are tested in the external validation. But yeah.
So point well taken, and the thing is, if a physician who is trained in the United States and if he wants to practice, he or she wants to practice in Africa, he might want to get trained in Africa as well, at least for a little bit, just to expand their knowledge base. And I will argue on the same line that your model needs to be trained on that data set before it gets now the issue of overfitting is surely a real one. But that's what this cross-validation is for, to do kind of like,
Yeah. So external validation is more to see if the data actually is some similar. If it isn't, maybe it's not going to work. I mean, it's possible. That's the kind of, if the data is very different between centers, that would be a problem, So those things. Right. So anyway, so those are real issues. This is machine learning issues, which are very important issues.
Mahfoush, I was also in Florida. I was very interested in your epicardial. Actually, this is epicardial fat, not pericardial.
Epicardial, yeah.
And we have done some study on that. And the very interesting things, what we found, first two things. Number one, there is a certain number above which is very abnormal and will be accompanied by a lot of calcium score increase. And we further checked the carotid intramedia stiffness and pulse wave analysis showed in this group with a high epicardial fat. And we find also 6 differences between male and female. And we reported that at the Europrevent in Malaga, Spain, not long ago. Have you found this information in your study?
I think, at this point, what I was showing here is just to make it very accurate segmentation of the images. So we're doing this kind of analysis as well, and we think we're finding similar. It was just that this study was just focusing only on making very accurate measurement of how much fat there is. But then, of course, you could use this measurement for all these clinical questions. And we're finding this, but it's like out of scope of what I was presenting here. So, yeah.
I think we should try and move on.
Move on.
Please.
One last question. Mike McConnell, Beverly. I'll just try to speak up. It was great data. One of the things I was hoping you could clarify a little bit is some of the studies you showed, you used features derived from the images, but others it sounded like you might have directly done machine learning on the images themselves.
Right.
Could you highlight a little bit which studies were which, or?
Yeah. So the deep learning studies were deriving the data directly from the images without any pre-computation. The other studies, we were measuring some things in the images with existing techniques and then plugging it into the machine learning. Yeah.
So I just want to keep us on time tonight. So I'm going to introduce our next speaker, and then I think we'll have a conversation at the end. We have time for more discussion. So let me introduce Dr. Yen, Albert Yen, from Meditex in Houston, is going to be presenting some data that he's done using the MESA cohort to looking at machine learning and improving the ACCHA pool risk cohort equations to predict cardiovascular events. So I'll turn it over to Albert, who's been a long-term colleague of Mort and I and others in the room. So thank you.
Thank you, Dr. Brewer. So good evening. So at last year's SHAPE Symposium, then the question was asked, can machine learning be used to improve cardiovascular risk prediction? And so this evening, I'd like to present the results of some work that that we've done to hopefully convince you that the answer to that question is yes, yes, I can. So several recent studies have shown that the current cardiovascular risk prediction in the United States, which is such as the 2013 pooled cohort equations calculator, can be inaccurate. And the result of that inaccuracy is that it can result in the overtreatment of low-risk individuals and the undertreatment of high-risk individuals. The problem with all those standard statistical models is they make a couple of assumptions. One assumption is that each risk factor contributes in a linear fashion to risk, and then another assumption is that all the risk factors are contributing to risk independently of each other. And so in reality, we all know that this is unlikely to be the case, so that those assumptions are false. And so that's where machine learning can show promise because it's very able to handle multiple variables, as well as being able to tease out the complex nonlinear relationships between those variables. So we chose for our data set that we were going to create a machine learning derive a machine learning risk calculator from. We chose the MESA data set. And as everyone knows, MESA is a well-established, well-known prospective cohort study initiated in the year 2000, comprised of 6,814 individuals aged 45 to 84. And then they were all the individuals were free of any clinical CVD at the time of the first exam. And there were 4 different ethnic groups in this cohort. And these individuals were all followed, they were monitored annually for incident CVD events. And the 13-year data is now available, and that's the data set that we use for our study. This shows an overview of our overall approach to coming up with a machine learning calculator. We first prepared the study data sets, and then we applied machine learning algorithms to that. So we basically used, we both trained our machine learning models and then tested it. And we used cross-validation and we repeated that whole process 10 times and then came up with our results, and then we compared the performance of our machine learning calculator to that of the pooled cohort equations calculator. So to prepare our study data set, then we started off with the full cohort, and then we removed 69 subjects that had missing risk factor data. And then we excluded 286 subjects that were aged above 79 years. And we did this because we wanted to make a fair comparison between the pooled cohort equations calculator and our machine learning calculator. And the AHA calculator was designed for individuals between the ages of 40 and 79. Then the last thing we did was we excluded 1,044 subjects that were already on lipid-lowering treatment at the time of their baseline examination. And so that we arrived at a final study population that was comprised of 5,415 subjects. here are the baseline characteristics of the study group, as well as the statin users that are shown on the right side. So once again, the statin users were not included in our study population, but I'm just showing you the characteristics of the. So in our study population of 5,415, you see that there were 381 hard CVD events, and hard CVD was defined as MI, CHD death, stroke, and then stroke death. In our group, and there were 775 that had all CVD events, and all CVD events were basically all the heart events plus other CVD events such as coronary cardiac bypass surgery, TIA, and other CVD events. So there have been many different machine learning algorithms that we could choose from. The one that we selected was one called support vector machines, or SVM for short. And SVM is a powerful machine learning algorithm that's very useful for binary classification problems. Basically asking, does a case belong to category A or category B? So, and given a training set of examples that belong to those two classes, then what SVM does is it finds this a boundary that helps to separate the two kinds of cases. So the example shown on the left, then you have circles and squares as there are two different kinds of classes that are in your data set, and then the SVM will try to find the optimal hyperplane. The boundary is called a hyperplane that will separate the different things. And so the cases that actually are very close to the hyperplane will have a direct influence on where that hyperplane is actually formed. And so those cases are known as support vectors, and that's where this technique gets its name. And the idea is that you're trying to find a hyperplane that maximizes the margin or the boundary, that maximizes the distance of those support vectors from the hyperplane. So the previous slide actually oversimplifies the thing, because we rarely can you actually just plot them and then draw a simple line and create your hyperplane. So in reality, then the decision boundary is most likely to be nonlinear, and so SVM is it's capable of mapping all these cases into a multi-dimensional field, and be able to create the hyperplane, which is actually a multi-dimensional hyperplane. So not even the two dimensionals that you see here. So another thing that we had to address when creating our machine learning calculator with the MESA data set is a problem with imbalancing of the data. And by imbalancing, what I mean is that the MESA data set is severely imbalanced in terms that there are many more of the individuals who did not have events compared to the number of actual ones that did have events. And so to address this issue of data imbalancing, then we used a method that was developed by one of our colleagues, Dr. Cacadeiras at University of Houston. It's known as NEATR. NEATR is just a kind of a cute name that he came up with for this method of filtering oversampled data using non-cooperative game theory. And so I won't begin to try to explain what that all means, but basically what NEATR does is it's a method of basically augmenting your data. So we have a case where we have only a few events compared to a lot of the other category, which is non-events, and we're creating new data, synthetic data that helps to fill out and more balance the numbers of events versus non-events. And so NEATR has been shown in published work to be able to increase the performance of your classifier, which in our case is the SVM model, but it avoids this problem, potential problem of overfitting. And so we were very careful. I wanted to point out that we only used NEATR. NEATR was only used for training purposes when we're training the model, and it was never done to create synthetic data for like prediction purposes. So we this is the part of the overall approach where we use twofold cross-validation. So we took the study population of 5,415, and we randomly split that data into two groups. So 50% that were going to be used for training, and the other 50% that we're reserving for prediction. And then we would, to the training cohort, then we would augment the data set using NEATR, and then we would train an SVM model. And I wanted to point out that to train our model, then what we're doing, we use the same 9 predictor variables. We didn't give our machine learning model any more information that we were going to get to give to the pool cohort equations calculator. And so then we train the model, and then we would test it on the prediction cohort and get results. And then we would flip those same 2 random groups. Then we switch places, and we use the other one to train a new model, and then we would use that model to test on the other side. And then this whole process was done 10 times, and so there were like a total of like 20 iterations of where we were creating like random groups. So this shows the characteristics of now looking at the not only the whole study population, but then also the subgroups where the results of how the pool cohort, the ACC-AHA calculator risk prediction compared to the machine learning risk prediction. So how did our calculator do? So let's take a look at the comparison. So this table shows like the sensitivity, specificity, as well as the actual numbers of false negatives, false positives, true negatives, accuracy, and net reclassification improvement. The top half of it shows the comparison between the AHA risk calculator for hard CVD events and the machine learning risk calculator. And you can see that our machine learning calculator had improved sensitivity, specificity, accuracy, and a net reclassification of improvement of positive 0.45. And although the AHA's calculator was designed only for prediction of hard CVD events, then we had data from MESA on the other types of CVD events, and so we went ahead and created a machine learning calculator to predict all CVD events. And you can see the comparison between the calculators for that too. So you can ask the question, then how did they do by gender? And you can see that in males and in females, then the machine learning calculator continued to show improved performance regardless of gender. Here are raw curves. Hard CVD events with improved area under the raw curve, 0.92 for the machine learning calculator, and the all CVD, 0.95. So getting back to clinically related issues is like you want your 10-year risk calculator to be able to help you decide if patients should be placed on statin treatment. And so we want to look at the standpoint of who should be taking statin. And so if you look on the left-hand side for hard CVD events, then on the machine learning of the normal pooled cohort equations calculator would actually recommend for 42, almost 43% of the patients in the cohort to be taking statin because it would classify them as being at high risk. And whereas our machine learning calculator only would only recommend 10.6%. Now, treating less patients is good in itself, but it wouldn't be that great if you were missing out on treating people who actually are at high risk. And so we looked at it from the other way, and we asked the question: well, how many patients are being missed if by each calculator? And so the AHA calculator would of the 381 heart CVD events that occurred in the study population, then 26% of those events occurred in patients that or individuals that the AHA calculator would have said no statin is needed, no statin recommended. And so, whereas our machine learning calculator, it was only 15%. So to summarize these results, then our machine learning calculator recommended less statin treatments and recommended less statin treatment, but also missed fewer patients and improved performance metrics as far as sensitivity, specificity, and area under the ROC curve. I want to bring your attention to another recently published paper that was from by Dr. Wang and his colleagues in the University of Nottingham in the UK, and they performed a similar study, and they applied machine learning algorithms. So they used clinic data that were available from over 300,000 patients in the UK clinics. These were family medicine clinics, I believe. And then they used they tried different machine learning algorithms, including random forest, logistic regression, gradient boosting, and neural networks. And their approach was to take 75% and train their algorithms on 75% of their study population, and then they would validate in the remaining 25%. And they actually gave access their machine learning algorithms. I gave them access to all these different to many other variables and any other variables, and let the algorithms choose which of those variables they wanted to use and they felt were meaningful. And they showed that they did show an improvement in area under the curve compared to the ACC-AHA calculator. Plus 1.7% up to as high as plus 3.6%. So in conclusions, we derived a machine learning risk calculator that outperformed the ACC-AHA risk calculator by recommending less drug therapy and missing fewer events. And some of the future directions that we're planning on taking, we are thinking about, well, we want to validate our machine learning risk calculator in other cohorts in different parts of the world, or also multi-ethnic cohorts, and possible. And that's one thing. Another thing that we're thinking about doing is to add additional risk factors. As I said, then we restricted our calculator to make it a fair comparison. We just restricted to the same 9 predictor variables, but we can add new variables, new features to the machine learning algorithm, and let it decide if which ones would be useful, and then maybe include newly discovered biomarkers. And so we feel like there's a possibility that as we introduce our machine learning risk calculator to more data, that the same overall technique, if given data that from patients that did have short-term events, then that short-term risk prediction may become possible. So the last thing I want to mention is that if any of these directions are of interest to you, then we are looking to, we will welcome your interest and in terms of collaboration. So on behalf of the other co-investigators, I thank you for your attention.
Open it up for any questions or comments.
As was mentioned before, you are putting a model and testing it within the MESA population, correct?
Yes.
Well, if there are unique characteristics to MESA, it's going, your model will fit better because the other one will fit in different data. Another alternative you could do is take the full risk equation and refit it using the same variables, using a logistic model. At least you would fit the coefficients to the MESA data, and it would be a fairer comparison of the type of model that you need.
I'd say that's an interesting thing. I think that's true. It might be something we do.
I was wondering, since your population is ethnically and racially diverse in comparison to many others, whether that has any impact on the model itself, or whether that is not a factor in the risk calculation.
I think we're helping since there was a lot of geographic diversity in the MESA data. We're hoping that increases the robustness of our model and its ability to generalize to other areas and include. And as you mentioned, the multi-ethnicity of the cohort is another thing that makes us hope that that our model will be able to generalize well to other areas.
So I have a question. So very impressive results. When you look at this different group, so one thing I just want to comment is that when you have this study where there's 300,000 cases, and your study was 5,000 cases, it is hard to overfit when you have 300,000 cases. Pretty much impossible. When you have 5,000, you should be very careful. So of course you use sample validation. That's fine. But like we work with SVM quite a lot, and there's very many technical details with it. So for example, like when you do this, like how do you find the parameters for SVM? Because SVM is not like a package that you just run it. You have to tune the parameters. So the important thing when you tune these parameters, the tuning of what's called grid searching and all those things, they have to be done within this tenfold validation. So sometimes people just by mistake, there's complicated stuff. When you do tenfold validation, you have to make sure truly there's nothing polluting this data, this 90% versus this 10%. And that includes the parameter search and includes feature selection, all those things. Because it is easy to misstep and do this kind of thing. So
but we didn't do feature selection because we only used the same features that AHA guidelines. So but you're right, when you do feature selection, then basically open a whole can.
Or like this grid search, like of the search of the parameters. Because there's like this, the SVM has these parameters you have to set. So the question is how do you set those parameters? And so that has to be done within the tenfold loop. So anyway.
Yes, you're right. You bring up a good point. I think one of the things that our colleagues at University of Houston, while we were doing the study, that they were very careful to wipe the slate clean between everything. It's like so that there would be no memory between any of the repeated iterations, that nothing was carried over from the previous model.
Question. So if you have a relatively small data set, let's say MESA 5,000, does that help you if you have, say, 100 variables, which you probably easily have from MESA, from clinical variables to biomarkers to imaging markers and many, many things you can pile up, which probably will help you for predicting. So
where is sort of the balance in terms of sort of total return, which you can match with, say, 200,000 subjects, but you only have 10 variables, versus 5,000 subjects, you have 200 variables. The total sum is the same, let's say, but how does that work out in terms of these two different approaches?
Well, I think that if I understand your question right, then actually, to answer your question, then I think that the number of variables that are involved in the equation, we basically limited our study just to these specific variables. But if we were to like include multiple other variables, then we start off with something called feature selection. So we basically wouldn't just we allow the whatever model we were using, in our case as SVM, but we would allow the model to help determine which ones are important to it and which ones are not. And there are different methods of determining which features, so that the variables don't become so huge and unwieldy. You're basically, the model is going to select which features are important to it as far as being able to discriminate one class from another.
Yeah, so the AUCs were incredibly impressive for just using those 9 variables. I guess kind of 2 questions come up. One is, a lot of us from prior basic data where the reclassification index using coronary calcium beyond kind of typical framing and risk scoring was very strong. So that seems to be the natural thing to look at, whether coronary calcium score would push that AUC curve. It looks like there may not be a lot of room to push it further. So I was curious if you've looked at adding coronary calcium as kind of the obvious first thing to add. And then how does this compare? Because there was a MESA publication looking at machine learning using all of the MESA variables for risk prediction. How do your findings compare to that publication?
Yes, thank you. So we have started looking at the effect of coronary calcium if you add it to the model. Some of our preliminary work shows that there is an incremental improvement in the performance of machine learning when you do add coronary calcium to the model. And so as far as the second half of your question was about.
Well, there's a publication from MESA where they looked at all the MESA data
Right.
for prediction. So how does this model compare to that?
Sorry, I don't know the particular article that you're talking about, so I can't address that. Matt, do you happen to know?
I don't know about the details.
I'm from Korea, and it's great talk, and I'm not familiar with this kinds of machine learning. But I have one question: is that the framework risk score and other risk score is not fit in your cohort. So if you make another classical model to predict cardiac death, and then have you ever compared your own model by using your code and then machine learning algorithm?
No, we have not done that. No, we haven't.
All right, so thank you very much, Albert. Great presentation and discussion. We'll move on now to introduce Dr. Greenland. I think everybody here knows Dr. Greenland, professor of cardiology and preventive medicine at Northwestern University's Weinberg School of Medicine. He's going to be talking to us today about the Precision Medicine Initiative. Thank you, Bill, for coming, and let you take it away.
So, good evening, everyone. Thanks for the introduction, Matt. So I'm going to talk about the All of Us research program, the precision medicine initiative that's being funded by the NIH. And if you want to take a break right now, this would be a good time to do it because I have no data to show you. The only thing that I have to show you is sort of the plan for this large initiative, which is intended to, over the next 4 to 5 years, recruit 1 million people and follow them for every kind of event that you can imagine, including cardiovascular events. So my goal here is just to introduce this topic to you so that it'll be familiar to you. And certainly if you want to sign up and volunteer, I can give you a card and you can sign up and volunteer. So I think this headline in the Wall Street Journal from January of 2017 sort of reflects the concept that Mort was talking about at the very beginning of the program tonight. And the purpose of this article was to get across the idea that if you collected enough data and if it was immediately being collected, so not something necessarily that you only collect once in time and leave it alone, like many of the studies that we've been talking about already tonight, like even Mesa, Framingham, that have multiple examinations, still those examinations are really far apart. But a project like what's being imagined here for this precision medicine initiative is that there might be sensors that people could carry around with them, that those data could be accessible to the research program. Those sensors could be obviously things that you already carry with you, your watches, your phones, you name it. So this article is imagining a future where your phone knows enough about you that you can ask this question: Siri, am I about to have a heart attack? And how would Siri know that? Well, maybe there's physiologic data that's being collected and analyzed, and in addition to all the background data that you have about yourself, what your lipid values were, what your blood pressure values have been, what your family history is, what your genetic makeup is, and so forth. So many of you probably know that Dr. Collins, the director of the NIH, is a geneticist. He's had a longstanding interest in the idea that was presented on that last slide. Could you actually reach the point where, with all of the data that's potentially available on a given individual, including ongoing data collection on a daily basis, could you get to the point where you could actually pinpoint in a precise way, so the name precision medicine, pinpoint who's going to have a heart attack? And that's, again, getting back to what Mort was talking about at the beginning. If you could really target an individual and say, you've got an 80% chance of a heart attack in the next year. That's very different than saying, 10% in 10 years or 20% in 10 years. And I don't know about your patients, but my patients sometimes say to me, 20% in 10 years, that's high risk. That means I got an 80% chance that I'm not going to have a heart attack. Those are the same people that go to the casinos who really don't understand probability. And that's how the casinos make money. Our job, though, is theoretically to do better than that, to do better than, a roll of the dice or, a spin of the wheel. So a couple of years ago, Francis Collins, director of the NIH, succeeded in convincing President Obama that what we needed in the United States was the American equivalent of the UK Biobank. And so I'll talk a little bit about the UK Biobank toward the end of the talk. But President Obama bought this idea, and the U.S. Congress and Senate bought this idea and have funded this idea. And in the 2015 State of the Union address, this is what Obama said. My hope is that this study, this precision medicine initiative, would create the architecture foundation whereby, and this is really why I have no data, because this is a study that's going to collect baseline data over the next 5 years, and then hopefully also collect enough events over the subsequent 5 years that we might actually have some findings to report 7 years from now, 8 years, 10 years from now. And this was announced in the State of the Union address in 2015, and it's become a reality. Data collection centers were funded initially in 2016, and then after a period of additional planning, those data collection centers have been up and going. And my role in this project is PI of one of the data collection centers in Illinois. So I just want to give you a brief overview of this. The title that Mort gave to this is the most expensive NIH study ever. It's not yet the most expensive NIH study ever. It's nowhere near as expensive as the Women's Health Initiative, which was probably $1 billion 20 years ago. So, but I suspect that over time, when all of the ancillary studies are added in and all of the data collection is accounted for, this will probably be $1 billion study, maybe more. The current allocation that the U.S. government has provided for this study is about $230 million. So it's a non-trivial number, and it's a reasonable commitment from the NIH. And the funding for it really comes from a special act of Congress, the 21st Century Cures Act, which was actually enacted just before the current presidential administration. So this was one of the things that got enacted before Obama left office. Let me talk a little bit about the UK Biobank, because that's not a dream, that's a reality. The UK Biobank was started about 7 years ago now. It intended to recruit 500,000 citizens of the UK who were also patients of the British National Health Service. And I'm going to come back to that point later, because that's a very important distinctive difference between the UK Biobank and the US equivalent. So 500,000 people were proposed to be participants in the UK Biobank. The UK Planning Committee spent 2 years piloting a variety of different strategies to initiate this study, and they piloted things like, could you do reasonably easily an electrocardiogram in 500,000 people? And would it be cost effective as part of a research study to do that? Or could you just rely on the data from the health record? And in the end, they decided not to include an electrocardiogram as a baseline measure. And I'll tell you that neither have we in the U.S. All of Us study. The decision was made that you could do some simple calculation. You're going to recruit 1 million people, and it costs you $25 or something to do an electrocardiogram. That's $25 million. And then ask yourself whether that would provide new information that we don't already know from considerably smaller studies, or you name it. So these are hard decisions. And maybe that's what some of the questions could be about later on, since I have no data. UK Biobank has succeeded in recruiting their 500,000 people. They recruited from clinical practices. And what they did in general was basically set up tables, not unlike what you're eating on tonight. They set up tables outside of the practices, gave people information about them. The doctors endorsed the participation in the study. People enrolled in the study using mostly paperless enrollment systems. And then they agreed to have some additional data collection, like a blood sample that could be stored as part of the biobank. Over the course of time, the UK Biobank has added additional ancillary studies and sub-studies to get some deeper phenotyping on subsets. So there's a study that got funded separately to do whole body MRI on 50,000 people out of the 500,000 people. And additional sub-studies have been added on, and we expect that the same thing will happen here in the US study. The US study was originally called the Precision Medicine Initiative, and I think some marketing person came along and said, that's a bad name. And so they changed it to another bad name, the All of Us Study. And that's what it's now called, the All of Us Study. And it ends up being a joke within the study, because whenever we want to talk about it, we say, well, all of us think that. And then we go, well, actually, what we mean is the people in the room here, not all those people out there that you want to recruit. But the All of Us study is the name of the cohort study. It's intending to recruit 1 million or more people and to follow them on an ongoing basis. And the follow-up in this study is not going to be like what you're familiar with the MESA study or the Framingham study or clinical trials. These people are not going to be seen again, most likely. They'll be seen at one examination, brief examination. I'm going to talk about it in a few minutes. And then the hope would be that the additional follow-up would be either from electronic sensor data or electronic health record data. There's two kinds of methods of engagement in the study. One is through healthcare provider organizations, and that's what our involvement is in Illinois. The academic medical centers, University of Chicago, University of Illinois, Northwestern University, Rush University, and North Shore Medical Center have agreed to serve as a consortium, and our job over the next 5 years is to recruit 100,000 people. To the best of my knowledge, none of us has ever recruited 100,000 people, but you know, we're gonna try to deliver on that. And there are 10 other academic medical centers around the country that have made a similar commitment and got funding to do it, and they are located in the usual places that NIH funding goes: the Northeast, Illinois, and the West. And there's relatively little funding for this study anywhere from Nevada to Illinois and from Illinois to New York. So you say, well, that's not all of us. That's certainly not all of America. The people who actually designed this study thought that it would be helpful to get broader representation well beyond people who are associated with academic medical centers. So if you were going to be asked, how would you recruit 200,000, 300,000 people in the United States for a brief examination, a blood sample, and a urine sample, and not have them associated with a major academic medical center, where would you send them? Well, you could send them to Walmart, right? You could send them to Walgreens. You could send them to other similar kinds of places that are everywhere. And the people who made the proposal were from Scripps in California, and their idea was to send people to Walgreens. And Walgreens has gotten on board with this. I don't know how many Walgreens stores there are, 5,000, 10,000, some huge number of Walgreens stores. And they claim that there's a Walgreens store within, it's almost like Walmart, within 10 miles of almost everybody in the United States. And all you need to be a participant in this study is to go online, sign up, fill up some questionnaires, get a referral to either an academic medical center or to one of the Walmart stores where you would get a brief examination, really brief examination, blood pressure, body weight, height, waist circumference, hip circumference, and then you're done. Blood draw, urine sample, goodbye. For now, but we're going to contact you again. So that's the general design of the study. So here's the list of things that we're getting: surveys, electronic health record data, we hope, some physical measurements, biosamples. The wearable technologies are currently a dream. It's not part of the funding of the study, but the hope would be that there would be access to wearable technologies and geospatial data that might come from your friendly phone. Another aspect of this study that is perhaps helpful to the SHAPE initiative is that unlike many other studies that we're all familiar with, the investigators who participate in this don't own the data. The NIH owns the data for this study. And so anybody will have access to the data. That's not necessarily true of the biosamples. Those are going to be highly competitive in terms of proposals because they're not renewable. The data in a de-identified fashion will be available to anybody, including your children, some kid in 7th grade somewhere who's got a bright idea, who goes on the internet, pulls down some data, and cures cancer. That's sort of an idea that gets talked about as part of this study. And if you're familiar with the UK Biobank, that's kind of what is available now in the UK Biobank. You can get access to the data. You don't have to be somebody who collected the data. If you want to get access to biosamples in the UK Biobank, you have to make a proposal, you have to come with funding, and so forth. So it's very similar here. The program includes a biobank, which is at Mayo Clinic. They built a brand new building. Picture what it would be like to house the samples for a 1 million person study. So there's 6 blood aliquots and 10 urine aliquots that will be derived from every participant in the study. And so they built a warehouse in Rochester, Minnesota that I've been told is about the size of 2 football fields. And it's full of millions of dollars of robots. And that's where the biobank is going to be. And again, if you're interested in some of these logistics, it's really fantastically amazing. Because the Mayo Clinic has contracts with virtually every hospital in the country for collection of samples and shipping to Mayo already. So Mayo Clinic has a contract with FedEx to go to literally every hospital in the country, pick up samples at the end of the day, get them to the FedEx shipping at the local airport, and get them to Mayo by the next morning before the samples expire, and as far as keeping them on ice and so forth. And another little tidbit that I learned about this is that in order to keep this from anybody from screwing this up, FedEx has a color-coded box that only goes to Mayo Clinic. No one else can use that color. No one. So I don't know what the color is exactly, but if somebody tries to use that color, FedEx won't take it. And furthermore, FedEx will come in and actually package the samples for you. So the investigators, we don't have to do that. All we have to do is get the samples to a central storage area. The FedEx courier comes in with the Mayo Clinic box and ships it out. And so biobank, there's a data center at Vanderbilt that is going to receive all the data. There are these healthcare organizations that I talked about, and then a number of other aspects of the study. It's a huge undertaking that's being coordinated by the NIH. This is a map, and so I wasn't exactly kidding. You can see there's a gigantic hole right here where there's no funded organization associated with the study. On the other hand, the red are the regional medical centers that have been selected. So Michigan, Wisconsin, Illinois, Pittsburgh, New York, Boston. What does that say? Southern. I think that's in Alabama. There's another one in Florida, Arizona, etc. So there's about 10 or so academic medical centers have been selected. There are a number of federally qualified health centers that have been selected. Matt, how am I doing on time?
Right in the 5.
All right. Okay. I think this is my last slide, so I'm good. So what I wanted to try to convey to you is the idea that, you know, this is an aspirational project. It's probably enrolled so far 8,000 people out of the million. That's more or less by design, the fact that we're starting kind of slowly. We're trying to test all of the procedures. In particular, the biobank. The biobank wants to make sure that every sample that's received gets handled properly. So they're kind of gearing up slowly. And the clinical centers have been added one at a time. We got lucky in Illinois. We got to be the last group to join to get on board with this. So by the middle of next year, by the middle of 2018, this thing will be at full speed, and we'll be recruiting over 100,000 people a year, more like 200,000 people a year for the next 4 years from the academic centers, and at least 200,000 people, hopefully, from the direct volunteers I showed you from Walgreens. A new model of research in terms of its openness, an aspiration to collect a rich set of data, and hopefully by collecting, you know, gigantic amounts of data on people and linking it to electronic health record, that this will create a new opportunity for precision of prediction and medical outcomes research. Now, getting back to something that Mort said at the beginning, if you wanted to predict heart attacks within the next month or 2 or 3, you have to have a lot of cases that occurred within a month or 2 or 3 of whatever data you were collecting. And studies like MESA, we have a few. I think maybe we have 20 people in MESA who had an event within a short time of the data collection. That's not going to get very far. And even if we get MESA and Rotterdam and Heinz-Nixdorf and so on and so on and so on, I think we did a table last year when we added all this up, and we still have relatively few cases that were of heart attack that occurred within heart attack or sudden death that occurred within a short time. On the other hand, if you add in the UK Biobank with 500,000 people, and now you're starting to talk about a relatively larger number of cases that occur, and then 1 million people in the All of Us study. Potentially, a research study could get enough cases and samples that you could actually, do the aspirational idea that Mort was talking about at the beginning. So that's my last slide. I'm happy to try to answer any questions as long as you don't ask me for any data. Apparently, I shut off any questions at all. Nathan.
Yeah, hi, Phil. Yeah. So that was a fantastic presentation, and actually, we're one of the Vanguard centers participating. I'm happy to say I've actually gone through the process as a participant. So yeah, it's I think a very important study.
So you're 1 in a million, Nathan.
Yeah, I'm at least 1 in a million, and yeah, I think it's a fantastic study for actually everyone to get involved with and to contribute to this important mission. There's a couple. Well, actually, one comment and one question. One comment is, certainly, at least what I've gone through, the consent process does require, a fair amount of technical skill in the computer. So, I'm concerned about being able to get a, representative cross-section of, people of all different socioeconomic backgrounds, perhaps, or skill, or, like educational, attainment, things like that. So that's one point. And I guess, if I'm not mistaken, they're still trying to maybe decide what they're going to ask at baseline, because the medical history was very, very basic, and in fact didn't even ask whether, I've had prevalent CAD or diabetes or, most other conditions. They think, maybe cancer, and if I smoked, if I use recreational drugs or something, very basic things. So I'm curious kind of at what stage the protocol is in place, and then also the opportunity. I understand there's an opportunity for like people like us around the table to provide input into maybe what measures should be done, what like perhaps biomarkers might be considered. So I just had those thoughts.
Yeah. So I mean, I was trying to give a fairly high level view of it, but your questions are very, very, very appropriate. There's been a lot of debate about what actually needs to be physically collected new from participants, because the study relies very heavily on connecting to the patient's medical record. And so one of the big discussions within the study is, well, if the data that you're interested in is already in the medical record, do we need to collect it again? Do we need to ask people about it? Do we need to, and which would be more accurate? The data in the medical record or the data that people would self-report? But what I just said also implies that we have actually access to the medical record and that it's comprehensive.
And if the participant is being examined at the same place to get their care.
Well, the issue here is whether it's comprehensive, okay? Because we know in America that people are not really part of a single system, and their record is not doesn't follow them like a National Health Service in the UK follows them. So it's a long answer to what the study has in mind to try to link all of the electronic health record data. But in simplistic terms, there's a belief that eventually systems could be built so that every person's electronic health record could flow into a single portal and be accessible to a study like this. Now, that would mean that the person would have to have an electronic health record everywhere he goes. Every encounter would have to have an electronic record, which is not true in the United States right now. So, I mean, if you dig a little bit deeper into some of the design features of the study, there are some questionable issues here. Some pretty questionable issues. I don't want to get too deep into it because I may say something that gets back to Dr. Collins. But, I think it really is a big question whether it's going to work. I think your other question was about, the complexity of enrolling. And that's also being discussed, pretty substantially, because what we do in other studies in order to allow people who are less technically capable, who are harder to reach, et cetera, is do a lot of hand-holding. And hand-holding is expensive. Okay, walking people through the enrollment process, et cetera. These are very expensive kinds of things to do. And this study is designed to be cheap per participant. And it puts a lot of the onus for participation back on the participant. And that's a disconnect from the concept of all of us. So, my guess is what's going to happen is that although they're talking about this as a, completely designed entity, it's probably not. And probably what will happen is by the end of the first year, a lot of things are going to start to shake out. They're going to realize that, hey, this doesn't work. We're not reaching the people we want to reach, that, we're asking the wrong questions. We're not getting the electronic health record data that we thought we were going to get, and any number of different concerns. And then you're either going to have the whole study fall apart or they're going to be redesigned. That's my guess.
Thanks, Phil. Great talk. Learned a lot from it. You might not know the answer to this, but I guess it's maybe an open question. Why 1 million people? Was there anything to drive that decision? Is that just kind of a sexy number? And of course,
it's two times 500,000,
right.
and which and so the UK is 500,000. So we're at least twice as good as that. So
there's no scientific.
Absolutely, as far as I know, maybe there's somebody in the audience here who does know, but I hope Dr. Collins is not listening to me right now. When it comes to the UK Biobank, I can tell you that the 500,000 was actually not a completely crazy made-up number. If you go to the protocol of the UK Biobank, which is online, it's freely available, anybody can read it, and what it says is that they picked this number of 500,000 because they estimated that by 5 years in, they would have 5,000 cases of coronary disease, 8,000 cases of diabetes, and so on and so on and so on. And so they said, if we have that number of cases and the rich clinical data that they presumably will have and the data from the biosamples, they believed that they had a large enough sample size to be able to answer some important questions. So, you could say, well, okay, it makes sense to have maybe even a bigger number and get those cases faster. But I don't recall that I ever saw any justification for the million other than it's a big number, sort of. In some ways, it's a really small number. If you're interested in diseases that are uncommon, 1 million people still, if you're interested in scleroderma, if you're interested in Parkinson's disease, a lot of different kinds of things. We'll be able to understand certain things about common disease pretty quickly, but like rare disease, unless they target it, which they say they don't want to do, which I'd like to do. Okay, some of us may go under the table and, recruit our favorite disease. But that's not what they're talking about.
Just a couple of questions. Sorry, a brief comment, if you don't mind, a quick question. I'm one of these people from the UK, Scotland in fact. I had a peripheral involvement in the biobank. We piloted ECG recording, decided not to do it because it's going to take 15 minutes for people to take their tops off, get dressed and so on, particularly older people. So it was abandoned from that point of view. Having said that, there are now ECGs in the biobank. I think they came from those having an MRI. And they wouldn't have time for an MRI, they had time for an ECG. But could I just ask, in Scotland, for example, every hospital admission is reported to a central point. So we can follow, if somebody dies, then we can trace the deaths and so on. We can all be linked into the sort of UK biobank type study. Does the same thing apply in the USA?
So we have something called the National Death Index. So deaths are reported, but hospitalizations, to the best of my knowledge, are not reported to any central location.
So if somebody has an MI, you may not know.
That's right. That's right. Yeah, I think there was a question here. Glad to see so much interest in no data.
This has a question. It's a question mostly for the group. I mean, you're talking about the percentages of cases in such a large cohort, but what's the number for predicting an MI within a year that it will be needed in the SHAPE initiative, such that the data will work out? I mean, what is that?
I can help Phil. We actually did the Excel sheet that Phil was talking about. We went around the world, everywhere, including the UK Biobank. The last number our Excel sheet reached somewhere around 1,200 people who had an event within months after their blood draw. One of the reasons we were very interested in machine learning is to make the best out of that. Obviously, the biggest challenge is for us to access those samples, blood samples, or plasma, or whatever, be able to run very sophisticated fishing expedition or survey of various things. We were talking about not only genomic, proteomic, metabolomic, lipidomic, go even microbiomic things that have not been touched, and just create a huge, massive amount of data. And then obviously the usual suspects, coronary calcium, traditional risk factors, and so on. And with that kind of machine learning and estimate data, I would say even this study would not be able to create in 5 years, 1,000 or 2,000.
Yeah, I think that's probably right.
And so really, the way to do it is just have to go knock on everybody's door around the world and collect this data.
Yeah, and for the SHAPE idea, you would hope to have very rich phenotyping of the participants. Not some fairly superficial level phenotyping. So I suspect that unless there's additional data collection that would have to be funded separately, not as part of the main study, there wouldn't be very deep phenotyping.
This looks, you just said that it was meant to be a cheaper study. This is the most expensive, cheapest study.
It'll be an expensive, cheap study.
Yeah. Thank you so much for sharing with us. We have the last.
Thank you very much. That's great. We're going to introduce our last speaker and then we'll have some open discussion. This is Dr. Kloner, Professor of Medicine and Director of the Cardiovascular Research at Huntington Memorial Research Institute, just up the road in Pasadena. Bob's going to talk to us about the insights into triggers of MI and CVD events, the straw that breaks the camel's back.
Thank you very much. I don't have any conflicts of interest. I think everyone here is well aware of the risk factors that might be considered chronic: hypertension, dyslipidemia, diabetes, smoking, etc. But there's been a lot less known about the concept of triggers and acute risk factors. So what is a trigger? It's an activity that produces short-term physiologic changes that may lead directly to onset of acute cardiovascular disease. And acute risk factors is defined by Toffler: short-term physiologic change, such as a surge in arterial pressure or heart rate, an increase in coagulability or vasoconstriction that follows a trigger and may result in disease onset. Now, there are a number of triggers that have been described associated with cardiovascular events, and most of these have to do with either emotional or physical stress. These include things such as the wake-up time in the morning. We know that there's circadian rhythms and that there's an increase in MIs between around 6 a.m. and noon, and this is also true of strokes. The day of the week, today's Monday. Seasonal variation, winter, cold, blizzards, and you might think that we escaped that here in lovely Southern California, but we do not, as I'll show you. The winter holiday season, coming up. Heat waves, infection, influenza. Some fine work by Mort, actually, on influenza and the importance of vaccinations. Physical activity, heavy, moderate exertion, sexual activity, psychosocial, emotional upset, anger, anxiety, bereavement, work-related stress, high-pressure work deadlines, which I'm sure we all deal with, sporting events, which I'll say a little bit about, lack of sleep, overeating. I always say it's a good thing we do our internships when we're young and not old. And then there's certain population stressors. This can include things such as earthquakes, blizzards, wartime missile attacks, sporting events, maybe terrorist attacks, high air pollution days, again, respiratory infection, flu season, certain drugs, cocaine, marijuana. So this is work by Toffler and Muller and others who really looked at and interviewed patients who had acute MIs and looked at what they were doing shortly before the MI and compared that to control times. And they found that about 18% of patients who had acute ST segment elevation MIs had emotional upset prior to the MI, moderate physical activity, heavy physical activity, lack of sleep, overeating, and then there were some others. And a good example of this was this paper by Middleman, who looked at episodes of anger as a potential trigger of myocardial infarction and found that if you had an episode of anger, you had an increased relative risk of having an MI at 2.5 in the first hour of the episode of anger, and then it was still elevated at 2 hours, but if you cooled off by about 3 hours, you were less likely to have an MI. And I always tell myself that when I'm driving on the 101 freeway or the 5 freeway to get down here to Anaheim this morning. Road rage is one of the triggers. So why is this? Why is stress a potential cause and related to these triggers? So we know that with stress, either physical or emotional, there is an increase in catecholamines, there's an increase in stimulation of the sympathetic nervous system. And this can have several adverse events. One is it can increase blood pressure, it can increase DPDT or contractility of the ventricle, this can increase oxygen demand, but it also may contribute to things such as atherosclerotic plaque fracture of the vulnerable plaque. You can also see increases in coronary tone and vasospasm with stress, which will decrease flow. With an increase in catecholamines and sympathetic nervous stimulation, there can be an increase in platelet aggregability, a decrease in fibrinolytic activity leading to a relative hypercoagulable state. All of these can lead to arterial thrombosis, acute MI, and sudden death, again suggested by Toffler, Muller, and others. Well, here in California, and for those of you out of state, welcome to California, we sometimes have a state of shock, and everyone who lives in Southern California is living on or near an earthquake fault line, and this is the famous San Andreas fault. We're somewhere down here. But this is the Northridge earthquake that occurred January 17th, 1994 at 4:30 a.m. I lived about 10 miles from the epicenter of that. And so at 4:30 in the morning, it sounded like a train went through our living room. Just about everything made out of glass broke. Our chimney fell over. Refrigerator ripped out of the walls. We had cracks in the walls. And it was probably one of the few times I thought I might die. I didn't die, but I can tell you that my heart rate was racing. And I'm sure that my blood pressure was elevated if I had been able to take it at that time. So with Jonathan Lior, who was a fellow in our lab at the time, we looked at a number of different aspects of the effect of the Northridge earthquake on coronary events. One was we canvassed 72 coronary care units in LA County, and we looked at the number of CCU admissions for MI the week before and then the week after the earthquake, starting on the day of the earthquake. And there was an increase in CCU admissions associated with this earthquake, an increase of about 35%. And if your hospital happened to be within a 15-mile radius of the epicenter of the earthquake, you were much more likely to see increases in CCU admissions for MIs than if your hospital was beyond a 15-mile radius. This was one of the freeways, which luckily I did not drive on. On my way to work, unfortunately, there was a police officer who was driving over this stretch of the freeway when it collapsed, and sadly, he was in this body bag. We did another study with the LA Coroner's Office looking at total death and different kinds of death. If you looked at January in the control years, 91, 92, 93, the number of deaths per day was pretty flat. But you can see that on January 17th, there was a big increase. Some of these were due to trauma. Unfortunately, that police officer who was in the body bag is part of this bar. But you can see things were pretty flat during the control years. But actually, there was a larger number of deaths related to atherosclerotic heart disease, as shown here. And again, the control years, it was all very flat. And if you went through these medical histories, most of these cases gave histories that were something like this. Earth started to shake, person clutched chest, fell over dead. It was very common. In fact, there was a significant increase in sudden cardiac death on January 17, 1994. We did a third study looking at all death certificate data in LA County. And you can see the control years here, 92, 93 are pretty flat, but 94 on January 17th, there was a significant spike in all deaths, deaths from heart disease, deaths from ischemic heart disease and atherosclerotic heart disease. And it's interesting that you see this spike, but then in the following couple weeks, there's actually a trend downwards. And so what does that mean? Well, one interpretation might be that you have patients who are at risk of dying and you hasten the death by maybe rupturing that vulnerable atherosclerotic plaque earlier than it otherwise might have ruptured. Another concept is that there might have been a preconditioning or a conditioning phenomena that occurred. If you look spatially, you also saw differences in deaths. This is average number of daily deaths due to ischemic and atherosclerotic heart disease in the days before the earthquake, January 1 through 16, 1994. And the highest number here is about 1.15 in the dark. And you can see here's the epicenter. So this is the control. This is the day of the earthquake. And you can see now the dark area here is, is 4 to 5. And the deaths sort of cluster around the epicenter spatially. We didn't see increases in other kinds of cardiac deaths, such as hypertensive heart disease, cardiomyopathy, death from valvular heart disease, or cerebrovascular disease. I'll just mention there have been now about a half a dozen of these earthquake papers in the literature also confirming these findings. This was a building that was not too far from where I lived. I also happened to be living in Boston from 1974 to 1978 and got to experience some very lovely blizzards there. This was a paper by Glass looking at increase in deaths from ischemic heart disease after blizzards. Death certificates in eastern Massachusetts were examined after 6 blizzards, 1974 to 1978. They were examined to identify effects of mortality from these storms. The total number of deaths was 8% higher in a blizzard week than in preceding and subsequent control weeks, 114 versus 105 deaths per day. Deaths from ischemic heart disease rose by 22% in a blizzard week from 37 to 45. The increase was greater in men than women. And since the increase in ischemic heart disease deaths continued for about 8 days after a snowstorm, it was felt that the effect was likely related to activities which might include things like shoveling snow, which you know can markedly increase oxygen demand. We became very interested in seasonal variation, the concept of seasonal variation of cardiovascular death. There had been some reports that deaths were more common in the winter due to ischemic heart disease, but most of these studies had been done in cold climates. We said, well, okay, what about Southern California, where it's usually a pretty modest winter. We don't get the snow and the very, very cold weather. So we looked at mean coronary deaths. This was from death certificate data that was averaged over 12 years, looking by month. And what we saw was a U-shaped curve here with the highest incidence of deaths from coronary disease in January and December, and then the lowest rates in the summer and early fall. Recently, Brian Schwartz, in collaboration with others and folks from Research Triangle Institute, collaborated with us to look at these same issues in a number of different states and a number of different cities across the United States: Pennsylvania, Massachusetts, Washington, LA, Georgia, Texas, Philadelphia. And no matter where we looked at it, we saw the same U-shaped pattern, which is seen here. So average monthly all-cause death rate and cardiac death rates seem to follow this U-shaped curve, where again, January and December seem to be the worst. This looks at, again, all-cause death rate, and we also find that this correlates with influenza. So as influenza goes up, so does all-cause and cardiac death. It inversely correlates with temperature. So the cooler the temperature, the more likely cardiovascular events occur. And one of the theories, there's several theories. One is that increased vascular resistance, more likely to have a thrombosis during the cold, increased oxygen demand as you're shoveling snow or going out in the cold. And then there were some other correlations here as well with dew point temperature, not quite as much with barometric pressure. Well, the holidays are coming up, and one of the studies that we did was to look at the total number of coronary deaths by day in LA County. And I can tell you that the temperatures, especially in December and January, tend to be pretty flat here in Southern California. But if you look at this data, you kind of go along here in November. Here's Thanksgiving, and then this curve starts going up. There's a peak around Christmas and a second peak around New Year's, and then it falls. And our group and Philip's group in San Diego have looked at this, and there actually is a significant increase with on Christmas Day as well as on New Year's Day. And there's a lot of speculation about why that is: stress of the holidays, increased intake of fatty foods perhaps, maybe excess alcohol intake, dealing with obnoxious relatives during the holidays. All that stuff can cause stress, so there can be both emotional and some degree of physical stress. Now, I want to say a little bit about sports. This is data from a paper that was published in the New England Journal of Medicine in 2008, and it looks at daily cardiovascular events in a study population in Germany during control periods, which are shown down here. And these red spikes are games when Germany was in the World Cup. And so there were these increases in cardiovascular events associated, especially with very intense games. Well, all right. So Game 7, I guess, wasn't that bad. Yeah. So we got interested in this concept related to the other kind of football, and that is, Super Bowl football. Again, intense European soccer was associated with an increase in cardiac events, less information about high-profile sporting events in the U.S. The purpose of our study was to determine whether there were changes in local death rates when a football team representing a local population, LA, participated in the Super Bowl. We analyzed death rates from LA County for the day of and 2 weeks after a losing 1980 and winning 1984 Super Bowl, and compared them with deaths for all other days from January 15th to the end of February for 1980 to 1983, and then for 1984 to 1988 control days. We also looked at other controls, including the same days of the Super Bowl and non-Super Bowl years. Now, the first thing we looked at was the Super Bowl, and LA has only been in 2 Super Bowls. One was 1980, and that was the Los Angeles Rams, and they lost horribly to the Pittsburgh Steelers. The Rams had been in LA for many years. They were a much-loved team. This was a very intense game. There were 7 lead changes. The Rams were underdogs. The Rams went into the fourth quarter with a lead, but then went on to lose, and the game was played locally in the Rose Bowl. In contrast, in 1980, the LA Redskins beat the LA Raiders, beat the Washington Redskins. The Raiders had been in LA for only a few years, and the Raiders had a victory from the beginning. They won by a large margin. The game was played out of state. It was a pretty boring game. So when we looked at mortality rates, all deaths during the control times versus the 2 weeks associated with the Super Bowl, there was actually an increase with this 1980 loss. There was an increase in circulatory death and ischemic heart disease death. When we looked at data from 1984, when the Super Bowl was played almost, just the same date, almost in January. But this Super Bowl was won, and it was a very boring game. There was actually a slight decrease in mortality rates, a slight decrease, although not statistically significant, in circulatory death, and no difference in ischemic heart disease deaths. Well, this was back in 1980, and the question is, would the same thing apply if we were to look at more recent Super Bowls? And actually, Brian Schwartz in our group recently published a paper where he looked at a number of other Super Bowls, some on the East Coast, some in the Midwest, and found very similar results from Super Bowls that had been played in the 2000s. Now, interestingly, there was a study that looked at fat intake after losing a football game. On Mondays following a Sunday NFL game, these investigators found that saturated fat increased 16% and food calorie intake increased 10% in cities with losing teams and decreased in cities with winning teams, and is unchanged in cities without NFL teams or in cities with NFL teams that did not play that day. Could that have played some role? I don't know, maybe. So our first Super Bowl studies were done in the 1980s, and again, we looked at more recent Super Bowls where, statins and antiplatelet therapies and drug-eluting stents are available, but pretty much saw the same findings. Okay. So I'm going to just actually skip to this part because I want to say a little bit about, is there something we ought to do about this? Well, there's no control randomized studies on this issue. I think that it would be good if there were. But just common sense suggests that we want to control all long-term risk factors for cardiovascular disease. We want our patients, of course, to be on statins for dyslipidemia and antihypertensive drugs, stop smoking, control diabetes and weight loss. Stress reduction, anger management, behavioral modification have been shown to work in some studies. Exercise programs to condition the heart, avoiding certain forms of heavy exercise such as snow shoveling, especially if one is deconditioned. Avoid overeating. Maybe slow, gradual awakening and gradual change in posture should be considered. And limiting time outdoors during high air pollution days. And of course, medicines, perhaps aspirin, beta blockers, calcium blockers, statins, or in some situations, prophylactic nitroglycerin. As Mort has studied and shown, flu shots work and will decrease the risk of cardiovascular events. And of course, devices, ICDs, public access defibrillators. And this was a study that was published by Blumenthal in 1997, looking at cumulative probability or proportion of event-free situations. Stress management was very effective in decreasing cardiovascular events. And then exercise was not quite as good as compared to usual care. And here stress management included exercise, meditation, massage, counseling, and this sort of thing. So in summary, stress, physical or emotional, can adversely affect the heart by sympathetic and catecholamine-mediated mechanisms. Wake-up time, physical exertion, emotional stress, overeating, lack of sleep may trigger cardiac events. Emotional and physical stress associated with natural disasters such as earthquakes, blizzards, the holiday season and intense sporting events can contribute, and recognizing the triggers, modulating stress, and treating with some pharmacologic therapies may reduce the effects of these triggers. Thank you very much. I'd like to acknowledge Drs. Lior Schwartz, Research Triangle Institute, who handled all the statistics for these studies, the County of LA, and the LA County Coroner's Office.
Thank you very, very much. We have reached to the end of our night, and a part of this meeting was to have interactive discussions and raise some questions, things that we discussed last time we were here. So thank you, Bob. We're going to run around. Matt, if you don't mind, start with your observation of what you learned tonight, and then we'll go Dan, and then circle around.
Obviously, some of the possibilities, I think, of machine learning is dramatic, and I think the two speakers who could have introduced me a lot better to what machine learning is and some of its capabilities. Of course, what's going on with all of us is tremendous, and I'll have to just see where that goes. Data free at the moment, but with great potential. I really enjoyed Bob's talk. I think I learned not to be a Rams fan. Is one thing. Take away the Rams are back. I know, that's why I'm really nervous. Yeah, well, that might be bad if they make the Super Bowl, right? It's going to be deadly. So, I don't know. I'm a little nervous about being a Rams fan these days. Given that, I think maybe Raiders might be a better way to go for longevity. We'll see. But no, I think the opportunity, and I don't know more how you're going to build in triggers and some of these acute effects that may predict short-term heart attacks. It might be tricky. Even with some of the great data you're planning on collecting, I think that's going to be a challenge that we need to try to figure out.
Thank you.
I guess I'm lucky my calcium score is low, because otherwise I couldn't have made it through the World Series. But it was a very interesting evening, and I think the whole aspect of the machine learning that was so well presented tonight is an obvious way of the future. And I think that's an exciting area for us to be focusing on with this initiative. I think the all of us, or like maybe it's the sum of us project is also phenomenal, and congratulations for getting it off the ground. I think that kind of thing, coupled with the machine learning, is going to give us a tremendous amount of information. I just wonder whether the United States, with our fractionated healthcare records and with the inability to really track information, is the appropriate place. I question whether something like Kaiser or Intermountain Health or some contained healthcare systems might be the better place to get your million people. And then just think maybe we're a few years ahead of time, because we think that these wearable devices and our 24 hours a day connection to our body's physiology and changes are going to dramatically change the kinds of data that will be coming in the future.
Thank you, Dan. Phil?
I don't have anything to add to those two.
Okay, sure. Go ahead.
It was a great opportunity to be here, and I think all of us learned a lot, and especially regarding the acute risk factors. For me, it was kind of a new concept, so thank you for the opportunity.
Thank you. Michael?
I did want to add, and I think, as you know, wearables, the technology-based center in Scripps, I think Fitbit recently announced that they're part of at least a pilot study, and I know we've done a little bit of advising on fitness assessment, and so I think that the opportunity is huge. The concern is, right, how much data are you actually going to have on each individual, right? So the emphasis on getting so many people but getting very little data about them, is the concerning part. And what it sounds like, from not having a very extensive survey, and so, it's really only going to be as rich as the data that you have about them. So that will be determined. But obviously, the machine learning side of it, is huge interest as imager myself, and being part of a company that does a lot of machine learning. And, particularly interested, the data around what was shown for, outdoing the AHA2017 risk score, just using the same data points, that would be a tremendous change in how we risk profile patients if that applied to broader populations. And I think we're really just starting to tap the opportunity of directly machine learning from the images themselves. So, yeah, lots to be done.
Thank you, Mike. You, of course, not many people know that Mike not only is a professor at Stanford, but also I don't know, call it employee or contributor to Google's life science initiatives. And can you tell us about where the industry in Silicon Valley, which amazingly, changed our world, affected so many things? Who knew that even the automobile industry was going to be just flipped all around by Silicon Valley? The health industry, do you think, is in the next few years, 5 years, 10 years, or 20 years? What's your perspective?
That's a big question. I'll probably mostly focus, maybe for the theme tonight, on the machine learning side, so that we have a collaboration and a commercial effort around machine learning from retinal imaging, so to make it easier to acquire the data and then automatic detection of diabetic retinopathy as the initial example. Jessica Vega, our chief medical officer, who's also a cardiologist, spoke to that earlier today. Actually, Microsoft also talked about a company that at least the data goes to the Microsoft cloud, that is set up with retinal imaging in the doctor's office, in a primary care doctor's office, for kind of easy access and rapid reading and diagnosis. We have a pre-publication on open access where we've looked at the UK Biobank data set, which still doesn't have a huge number of outcomes, but we looked at how good a retinal image is predicting cardiovascular events as a single test. So again, the data is still not as robust as we'd like, because you need more events to train well, but I think that's another example where, as was shown today, where you raise what things are going to replace the doctors. I think a lot of it is initially supplementing or enhancing what physicians can do to spend more time than trying to communicate the results and guide treatment. But I think a lot of the imaging-based things, there will be a lot of extra information and extra risk prediction that we can add to through these technologies.
Thank you. I want to add something at the beginning, the question of the session, that whether cardiologists will be replaced or physicians. The analogy of internet, the IT world, it didn't put engineers out of business. In fact, created more business for engineers, more opportunities. Physicians will have new things to do. For particularly primary care physicians, family physicians, they will be empowered by technology and do the kind of things that specialists are doing now by the new automation and machine learning and artificial intelligence and so on. Do you agree?
Well, I think that a lot of the diagnosis part, diagnosing skin cancer, diagnosing retinal abnormalities, and as that expands to cardiovascular imaging and analyzing large data sets, computers are just going to be better than humans at that, and they're much more consistent too. And particularly as you want to expand that across the world and not just in high, payment areas for healthcare. But there's still a lot more than just the diagnosis to healthcare.
Sure. So. Thank you. Dr. Tao, any comment?
Okay, I'm coming from China, so I would like congratulate for your wonderful
organization meeting. So we learn a lot of the multi-layer technology, especially for the machine learning. So in my opinion, this machine learning could be have a bright future, but we need multiple discipline cooperation to demonstrate this is the case. But I believe if this learning machine will be successful, will improve our the health without the big disease. We will live a long guarantee and enjoy our work and life. So we hope this wonderful and future landscape could be coming as soon as possible. We are waiting for this wonderful time. Thank you.
Thank you. Any other comment? Any comment on this side? Any other comment? Please go ahead.
I've done a little bit with risk modeling, including with the traditional risk factors. And sometimes it seems like these traditional factors we know so much about that sometimes the simple linear models work very well. So I'm surprised to see that it worked so much better using your support vector machine. I've used boosted trees, for example, and found a few interactions, but it wasn't a big deviation from the linear models. I think there will be more potential with more sophisticated systems like ECGs, like the imaging, like maybe all the genomics and metabolomics or proteomics that you can collect. And that's really where the complexity comes in, and something that's nonlinear will come out. The other thing I just wanted to mention, of course, is that you're all talking about prediction now. It would be nice to be able to harness some of this to get at the causal factors as well, but then it becomes trickier because you've got to be able to identify something that you can target for a treatment, which is another aspect.
For drug development and developing new therapies as well. Sure. Jim?
I came in on the tail end of things. I had another meeting I went to, but I can say that you continue to put together terrific programs with very interesting people. So that's one thing I noticed. Second, with the variety of technologies that have been presented over the years here, it seems to me that there should be a multiplexing type of approach where every type of tool improves the pretest likelihood for the next thing. When you look at disease processes in multiple ways, in different ways, from an imaging point of view, from a physiologic point of view, from risk factors, from genomics and proteomics type of thing, ultimately you can start to define a class of people that you can get a very nice predictive model. So, and I think for investigations, for example, let's look at the AFCAP TextCap study. Imagine if you then took that population and only studied the effect of statins on those who had a coronary calcium score greater than 200. You know, what would be the thing? So it's in an analogous way, some of these things that we're looking at, if we could only study people who fail one test first and say, this is a group of people that we want to now see the effects of therapeutics, we'd start to have a much lower number needed to treat and really defining things. So I like the variety of the presentations. I particularly enjoyed because I caught the whole amount, the talk on triggers was very exciting.
Thank you. As you know, machine learning is good for doing that. That, just like she said, very complex. You got ECG, you got imaging, you have clinical data, and you put them all together and try. Can we go here, Mike? Let's just start. Mike, I think you've been here from the beginning, and they even showed some of your data. And our machine learning paper that Albert presented was based on SVM. The British group that showed a small amount of incremental value did not use SVM. However, the New Zealand groups that presented a year before, they would use SVM, and they showed significantly larger amount. I don't know, Piotr is the best person in this room to know about machine learning, but there seems to be a better yield coming out of this method of machine learning, and you have a large data now, like 60 some thousand cases and so on. If we walk us hypothetically how you would wish to see machine learning come to aid developing a new composite scoring way.
Well, yeah, I'm certainly no expert in machine learning, but one of the themes here, I guess, is like you said, the better the phenotype, the better, the more data, the more accurate, the better. So what I'd love to see machine learning do is, in the future, take not just one-time risk factors, of course, like we have in our data set that we talked about, but some form patterns out of changes in risk factors over time, even from my one visit with my patient to the next visit. That's where I think there would be a lot of patterns we pull out, not just from the static baseline risk factors, but just this discussion of kind of do we want a smaller cohort with great phenotyping, or do we want a massive cohort with minimal phenotyping? It's fascinating to me, having grown up with things like MESA, with cohorts with extreme phenotyping. And just that's why I wonder. I think machine learning is going to bring the most to bear on a very highly phenotyped cohort, and it may not have as much value on. You can link that with the acute trigger talk. A lot of those things are random events. I mean, I guess you can talk to meteorologists about predicting blizzards and whatnot, but I just don't know how. Let's say if we in an all study we gather some data on at a baseline visit, I just don't know how we're going to get any better predicting the acute event without a lot more data to form patterns from. So I'm still very conflicted about this idea of larger study, less phenotyping. But what I love to see is start to form patterns with changes in risk factors over time, or change in activity level steps, heart rate trends, all these things. That's where I think the patterns will be formed.
You think we just gather, instead of 1 million, 10 million people every day, every morning, their heart rate, their temperature, their pulse ox, and so on? Would that really help us in predicting biology of MI and all of those things that happen at vulnerable plaque and blood level?
Well, right. I would rather see less patients with more phenotyping.
With more phenotyping.
I just 1 million, 10 million, 100 million. I'm not sure. I'm not sure if there's a number there. But yes, I think there is. I think there are patterns in vital sign trends and in steps and sleep and all. I think there's a lot of patterns there that we don't know about.
Thank you. Any comment?
I'll only say that I'll comment on the acute triggers, because that's my area of work, and I'm looking at it a little differently. So where we built a cohort, and as Mike was saying, that with very few patients but are very exquisitely phenotyped. And I think you need to be careful about phenotyping the outcome. So we're looking at thrombotic myocardial infarctions like type 1 MI versus type 2 non-thrombotic, which is probably the greater half now in the hospital. And, I think that all these traditional risk scores and risk factors are predicting the substrate. They're predicting how likely you're going to develop atherosclerosis, where there's very little to nothing in these risk scores that give you the other half, because just having atherosclerosis is not enough to have a clinical event. You need plaque rupture and you need a pathological thrombus. In fact, the pathology data tells us that even having a plaque rupture isn't enough. Most of those heal over just fine. And the ones that lead to sudden cardiac death can be as benign as a plaque erosion. So I'm looking at it a little different. I wasn't expecting that talk because I was biased coming in. But I think that it's also very interesting what the risk factors are for the trigger that will set up the storm to have a pathological thrombus at a real event.
Thank you. Any comment?
Sure. So a couple of comments. One thing, I think from my perspective, the most important thing for us to work on those things is the access to data. And what I've learned, here in other meetings, we are fighting with IRB to get access to 10,000 cases. All are de-identified, and we're going. I mean, the amount of work we have to do to get access to data is amazing. Then I hear there's some company here going with insurance, and we're buying 20 million cases, and they're doing research on it. And then I ask, well, Did you get IRB? Well, that's the identified data. We don't need an IRB. So there's seems to be some different levels of this, and I think we have to figure out that if we deal with the identified data, we have access to it, because this is hindering. I mean, it's in the end, it's killing people because we can't access the data. There's no reason for that not to, and I think this pendulum has moved in too much into that direction of protection, and it's very difficult to do what we want to do. So that I don't know who has power. I certainly don't have power. I just work with algorithms. But if we get more data, we certainly can deliver better results.
As you know, this is actually, there's a fierce competition in accessing data. I know IBM acquired another company. Anybody from IBM here? Their vice president was going to join, and so they were telling me that they have 85 million data. So Phil, you're going to get 1 million to connect. They're saying they have 85 million live data of EMR that their machine learning and their Watson can go through and swim.
But there was an abstract here that was saying that they're getting 20 million cases.
Yeah.
Insurance companies, they have this kind of, and somehow they buy it.
Yeah. Please go ahead.
I'll just make a comment about that. I mean, the quality of that data, very questionable.
That's right.
And there's no control curation of the data. There's no quality of assurance of any of that data. You have to be really careful, be impressed by those numbers, because it may be a lot of garbage.
Yeah, it's true, but sometimes the quality can be also automated. You could probably pull maybe 10% of the data, which is very good, and so forth.
Yeah, but if you start with garbage and then you're going to clean the garbage, and then try to learn something from clean garbage, at some point you get distance from true signal there.
Any comment? Yeah.
I mean, just a small comment on this SVM issue. So we work with this tool for quite a while. We actually worked with the design, the developer of SVM in Taiwan, and this is method from 20 years ago. It's a very valid method. It's not. It can happen. It's a tricky method in terms of overfitting. So because we work with this, I kind of know that.
Yeah, we actually did. So as I said, the asymmetric type nature of the data, where you have a small amount of event and you have to oversample the other group. We did different methods. They didn't work out. Right. The only method that worked out was the one that Johannes developed. So
sometimes one other thing is there's these packages where you have 100, 200 different machine learning methods, and there's actually ways you can run 200 different ones in a batch or go home and get it done.
Well, we would run this 1 week and we would come back next week to get the data. So this was not something that you could do. This SVM that you saw, Albert and I and the U of H team, we probably had 40 meetings over a year and a half. It was just every time we would say, okay, no, we can't take this, go change it. And we'd have to go 1 week back because their computer was just crunching the entire week to run that.
So sometimes the one word of caution is also that you can by chance find the best methods on this data. And that is kind of other type of overfitting by just trying many, many different methods. And then you say, oh, well, that one works the best. But then you take some other data set, it doesn't work. So actually, we found that sometimes linear logistic regression works pretty well. It's true. There are data sets we have where you can't beat logistic regression. And depending on it, for some data sets, it's very clear, clear statistical difference. So there are cases where just a good old logistic regression is it's a form of machine learning too. It's just depending how you phrase it.
Thank you. Next person.
Thank you. It's a wonderful meeting. I learned a lot.
Thank you.
I'm an imaging cardiologist, and I see a subclinical disease just about every day. So my question is, although I see a lot of work really using mortality or cardiovascular mortality as an outcome, is there a way that we can actually shift our attention to use the development of atherosclerosis as an outcome, a variable? And because ultimately we want to eliminate that, so that we can actually eliminate the downstream outcome, right? And so I think at some point, nowadays we have so many tools to detect, to measure precisely the burden of subclinical disease. Why not we use that as a outcome, predictive outcome, so that we can assess the risk of developing, the first step of the disease before we reaching too far. To me, that predicting death is a bit too far, too late. How come we just stop at the earliest stage? Perhaps we should think differently downstream once we have better methodology. But I clearly see this is the beginning of the new era of developing, advanced tool. But I see that once we have the tool, perhaps we'll have to shift our thinking into a different stage.
Sure, you're absolutely right. But we are dealing with a mammoth problem. It's not an easy thing. When they compare the Amazon group, the tribe, and you look at the U.S. coronary calcium, it's a huge difference. In the U.S., after age 50, almost like 70% of people have coronary calcium, whereas in the Amazon tribe, the study was, I think, published last year, they were just mad. What, like 15%? It's just an incredible difference between the two. Now, AHA spent entire time on this. In SHAPE, we really wanted to get something different, something that not been done before. The short-term risk prediction, the vulnerable patient, identifying people who are going to have an event in the year or months ahead, would give a new opportunity to cardiology that we never had before. We may not need to do a lot. We may not even need to develop new therapy for that. If we have this high risk, I had the chance to chat with Dr. Brownwell on this. He said, I will put, if you tell me he's going to have an event with 20 to 25% a year, I say put him on cabbage. This is a man who spent his life in cardiology, because this is new. We don't need to develop a new therapy, or just tell these people that they're going to die. They will make some changes that otherwise they won't do. But you're absolutely right. Primary prevention, early stage, all the way to childhood level and social level, will have an overall greater impact than individual. But that's the area that we've focused on that hopefully will make a difference. Thank you. Any other comment on this side? Anybody else?
Yeah, I just had a few short comments. I think, I was extremely impressed by, your MESA results with the actually machine learning. And I think as you are able to get a large enough collection of data sets, it would be, really interested to see if you can come up with a simple set of measures that can be applied in, like regular clinical practice that will predict, a short-term risk of an event. So that's going to be very important. And the other comment I had is, I guess it's not clear to me exactly if eventually you're going to be able to, we're going to be able to have from machine learning a relatively simple equation that can be put into some sort of calculator where where you are able to use that at point of care to determine someone's risk. So I guess maybe that's I guess one of the next steps.
Yeah, Nathan, that is really our focus.
Yeah.
And we're learning that it will not be one equation. We may even have 50 different models for different areas, different geographic or different ethnicities. That's just our current thinking after looking at data, looking at all the things that in other countries are done. But that's fine. Computer, machine learning, so easy for them. You just enter your information, identifies which algorithm and which function would be best applicable to you, and use that. So it's not going to be just like a Framingham risk score or the equation that we have
That's
approved.
fantastic. Yeah, I think that's a fantastic vision that you all have with that, and it'll be great to see how this is eventually implemented in clinical practice. And then I guess the last point is this: we haven't talked about some of these more novel biomarkers that have been used in certain laboratories are developing, such as GD Biosciences and the pulse test, and maybe how this might further help improve risk prediction for short-term ACS events, and maybe how that, because they've used machine learning in that approach too.
Nathan, that is part of our proposal for the SHAPE project, that if we get it funded, we will be measuring those and many other things that hopefully we can get in that blood sample. Thanks so much. Any other comment? Bob? Oh, please go ahead.
Thank you.
Please.
It was a wonderful program, and I learned a lot from machine learning. I might have a question for Dr. Slonka.
Okay.
Yeah, regarding the methodology. So, for most of application of machine learning in predicting events, I saw the outcome are in binary or classifier format. Or I know machine learning can be used in linear outcomes. But there are, as far as I know, there are only the random survival forestry methods that could be used in survival data. So is there any updates of method in machine learning that specifically for survival data or other form of clinical data? And if no, is there any obstacle for scientists to develop such method?
So there's two aspects.
Microphone, please.
Yeah. So one is the first part of it. You said is binary. It's not really binary because it's probability. So it's a continuous from 0 to 1. So like when we show arrow seeker, it's not that or no that. It's a probability. So that is one point. But the other point you mentioned is a different point, and that's a question of time to event. Because what we do here, typically machine learning methods, when we use them, they don't use time to event. They use yes or no fact. So you can censor your data at some age, and then but you still don't account exactly for time to event. There are new methods. This is very new thing that they put like in R and all that. They have methods to do like boosted survival curves, where it's like a form of machine learning. There are methods like that. We readjust. That will be more important for the longer term. For short term, like this 1 year, I don't know if it's very important, if you want to adjust for this. But this is an adjustment which can be done in machine learning, and there are things which people are developing to account for that. So.
Thank you. Any other comment? I'd like to have ask Bob to close the meeting.
Well, thank you very much, Mark. I've learned a lot tonight. I didn't know very much about machine learning. I think it might be interesting to see whether some of these triggers should be entered in some of your models, especially the seasonal one, because we know that everywhere we look, there's about 25 to 30% more infarcts in January and December. And I don't see that that's been incorporated in anything. It might be something to think about in the future.
It's actually, I have a friend who works in machine learning with police data in Chicago. And they found that the police department came to them to find out what's the crime prediction, how to predict where it's going to be more crime so they can send more police. And they found actually the weather was the biggest predictor, and the police didn't like it at all. It was like politically not a good thing. But they say in the summer, like it was hot, then there was more murder.
That's right.
So it reminded me of that.
So
definitely,
the summer is less MIs and more murders.
It has been used for that.
But again, thank you, Mark, for putting out a great.
Thanks so much. Thanks, everybody. Thank you. Thank you very much. Thanks to Matt and Dan. Thanks so much. Thanks, everybody. Have a good evening.
certain point.